So in a previous video, we talked about how you can scale up your database. And one of the techniques that I mentioned is something called sharding your database or sharding your data. Let's dive into sharding, why you'd use it, what are the pros of it, what are the cons of it, and then also what databases kind of provide this out of the box. Because some databases like Postgres might be a little bit more challenging to shard data compared to something like MongoDB or Redis, etc. So typically, a user is going to make a request to your API, and you have one database that can scale up vertically and handle a ton of traffic. But at some point, you may reach a threshold where the amount of traffic or the amount of CPU or amount of memory going to that one database is just not going to be able to handle the traffic. And so one technique that you can do is you can actually take your data and store it into different shards. So I'm going to say shard 0, and we'll say shard 1, like this. So now when a user tries to insert a record or read a record, there's going to be something that is going to be deterministic to say that, okay, this user record is always going to be stored on shard 1, so that in the future when we try to fetch back that info, it's going to also reach back to that database. And you can imagine this is going to put less strain on that centralized database, and now your data can be spread out into many different shards. You can even have 3, 4, 5 shards depending on how large your data is. Now, one good use case of when you might want to shard is if you want to put different tenants specifically on different shards. So as an example, we can just go over here, put some data. We'll say like an org ID of some UID. Just imagine this is a UID. I'm not going to type out a full UID here. And we need to basically run some type of algorithm to hash this string and bucket it into one of these shards. So the naive approach might be something kind of like this, where you have a method. You can pass in a string, and it's going to basically run a hash on that value, and it's going to bucket it to try to determine what database it should live on. Now, this is a naive approach, and we will dive into more detail of a more elegant approach for how you can determine where this primary key or this shard ID should live. But overall, it's going to return back a number, 0, 1, or 2, but it may determine that the organization of like Pizza Hut should live on this shard 2. And then adding in another org such as Taco Bell might live on shard number 0. And from now into the future, every request will just make that organization's data live on that shard. Now, like I mentioned, this is the naive approach because there is this need as your company scales, you're going to want to add in more shards. Let's say you want to add in a shard 3 or a shard 4. When this happens, you have to basically look at your existing data and try to figure out how to redistribute it to this new shard, because you may have tons and tons of tenants living on these. You made a new node. Now nothing is being added to that new node. And this is where sharding gets a little bit complicated, because in order to relocate all this data, you'd have to run some type of background process or lazy migrate it over to the new shard when people try to read or write into the old shard, which, as you can imagine, when you know anything about hashing, if you were to add in a new DB over here, so DB4, it's going to completely change all of the distribution of where this data lives. So it may determine after you add that shard, it has to put Taco Bell over here and Pizza Hut needs to go over here, and maybe some third organization needs to go over here, which can become problematic because having to rearrange all that data is computationally expensive in terms of the network and also just accessing and reading from the database. So one approach that you end up doing is something called virtual buckets. So instead of having that hard-coded list of 4 databases at the top, you just go ahead and take your hash of like, I don't know, Pizza Hut, and you mod it by some arbitrary large number that's hopefully larger than any of the amount of shards that you need. So in our case, we only have 4 shards, but we're still going to use a really large modulus number so that it's going to distribute this into some of our virtual buckets. So let's talk about virtual buckets. Behind the scenes, you'd actually have like a range. So like, for example, this could be bucket 0 to 400. This could be 401 to 800. And then this one could be 801 1023. So with the virtual bucket approaches with the ranges, when you do this math, you'll determine, okay, maybe this one needs to live on this bucket, and this bucket could actually point to shard 0. Another one could point to shard 1. This one could point to shard 2. And then as you add in a 4th database, you basically just scale the ranges a little bit. So this one would actually be like to 300. This one would change from 300 to maybe like 700. And this one would be like 924 all the way to 1023. So, but again, the idea is that we kept this number consistent. And so it's always going to hash the exact same bucket. We just scale down the number of shards that fit on this bucket. So there's a less chance that the data needs to be moved around. Okay, we still have to move data around. We have to shuffle stuff around and redistribute it. But we could do this a little bit faster. We could do it as a background process. And we could also have some lazy migrations in place to kind of move data to its new shard on new writes or reads. So hopefully the pros of sharding is obvious. You can fit more data. The latency is reduced because you don't have one database trying to handle all this traffic. You can distribute the data across many databases and maybe even co-locate some data so that the user can get the data back faster that they're interested in, right? You could probably even shard by region if you wanted to. So you can have all the data that's in a particular region be sharded together. That's another approach. But let's actually talk about some of the cons. So the first con is when you shard, if for some reason you do have data that you need to join across shards, it adds a lot of complexity because typically your API has to then fetch back data from one shard and then from the other shard and join it inside of the code itself. Unless the database is smart enough to handle this type of stuff, which many are, like if you have a database like Redis or MongoDB, they have a clustering option. You can just provide shard IDs and they automatically do all this stuff for you. But I do think the joining, but I still think a lot of the joins has to happen in your application logic. Also, transactions across shards gets really complicated. Like if you wanted to transfer money from this person to this person, they live in different databases. You'd have to make sure that somehow you have like a top level transaction that's keeping track of that. So if it fails, you can roll back from both the shards. So hopefully you can see how a transaction would be kind of challenging because most of the time a transaction works on a centralized database, but now it has to run over many different databases, which is just challenging in itself. All right, here's a big obvious one. Migrations become more challenging. Instead of just running a migration script on one database, you now have to run it on every single shard. And how do you coordinate that to make sure that, hey, the data that's being fetched on that particular org, has that database actually been updated? Is the API trying to do the old approach to the data or the new approach? So coordinating those migrations across the shards can become pretty challenging. If you can imagine, doing automated backups and restores become harder because now it's just not one database you have to back up nightly. It's many databases you have to keep backing up. And then if one were to go down, how do you back that up? We did talk about rebalancing is hard. So I'm going to kind of skip that one, but that is just something that you have to think about. How do you rebalance data when you add in a new node, or if you remove a node because you lost clients or you have to shrink the data? Removing a shard also requires rebalancing a bunch of data as well. And for the last one, I'll talk about choosing the wrong shard key can create hot shards. So I'll kind of translate this to when I was working with DynamoDB. When you have a PK that is being used by a bunch of data, what it ends up doing is it puts all that data onto the same shard or the same partition, right? We call it a hot partition in DynamoDB, but DynamoDB also does sharding under the hood for you. But if you have all the data being put on the same shard, you're back to square one, where all of the compute is putting a lot of strain on one database. And if you don't properly set the keys that you're sharding by, you're back to square one with having a bunch of complexity with all these shards, but then also this shard just has all of the data. So when you're designing what to store, you need to make sure that you're using an ID that's very unique and also won't just group a bunch of data onto the same shard as well. So that's about it. That's the overview of what sharding is, how it works, the pros and the cons. I would say if you do want to do this, there are databases that have this out of the box. Like I mentioned, MongoDB has a shard ID built into it. You can actually set up a cluster of machines that automatically have your data be distributed. DynamoDB is also a database that just scales for you automatically. As long as you have a good partition key, it's going to scale out all your data. All right, anyway, that's all I wanted to talk about. If you guys enjoyed this overview, let me know. Leave a comment below if there's something I need to dive into to explain more, or you can just leave a comment of a new video you want me to make a video on. Have a good day and happy coding.